you first for the invite. It's much appreciated, and thank you all for attending. So what I will be presenting today is a method to cluster scenarios, right? So scenarios are oftentimes a really useful piece of methodology, right? That is used when we are dealing with uncertainty or trying to formulate uncertainty in optimization settings. And this was work that was done in terms of trying to identify efficiently patterns among the scenarios, and then how to use those patterns to derive bounds, right? So this is kind of the talk today. Okay, so this is my plan, and I just need to make sure that I don't go too much over time. So I will just provide a brief problem statement, general problem statement. And then I will recall what cluster analysis is, right? So oftentimes, and maybe most of you have some experience doing clustering analysis. But I just want to recall a little bit what that is, and maybe use a very nice paper that is referenced at the end that presents a more mathematical programming view of clustering. So in terms of the modeling, first modeling what we are interested in clustering, right? Modeling the problem, which then helps us really understand what is being done in terms of the methodology. Then I will talk about what we propose, this idea of decision-based scenario clustering. Then go into some general bounds, right? So how the clusters can actually be used to compute efficient bounds for stochastic programs, and then some concluding remarks. Again, I don't know how you guys proceed. I can take questions as we go, or at the end, it's as you wish. I'm totally open as we go. Okay, perfect. So please, feel free to ask questions as we go. Okay, so this specific piece of work was done in collaboration. I'm just mentioning here the two colleagues with whom I collaborated on this project, right? So Janos Schaffman, who is one of my colleagues at ESG-UQAM, and Mike Hewitt, maybe some of you know him, from Loyola University. Okay, general problem statement. So we consider a probability measure P, right, defined over a probability space and a decision set. Okay? And we're trying to identify, right, the best solution, Y, right, that minimizes some function phi that is defined using the probability measure. Okay? So kind of a very general problem statement that is often applied in optimization under uncertainty settings. Okay? A natural choice for this function phi here is often to use the expectation. That being said, can be other, so we could certainly use the expectation. We could also use other functions, right? Value at risk functions, et cetera, et cetera. Okay? So if we take, this will be the function that will be considered in this talk, right? So we're optimizing based on the expected, on the use of the expected function. And what we have here, right, is this function g here that enables the evaluation of a specific solution Y under a given realization considering the probability space. Okay, so and so we're basically just optimizing, trying to find a Y that minimizes the expected value. Okay, so this is kind of the problem. Oftentimes, and this is where scenarios enter the equation, right? Is that in order to be able to solve problems, we need to discretize, right? We need to generate. Oftentimes, a number of realizations might be infinite, and so forth, right? So we need scenarios in order to discretize to be able to then solve and obtain a solution. Okay, so if we do this, we start from this perspective here that we've generated somehow, right? Using different techniques might exist in order to sample the realization the realization set, right? And we start from a set big S here, and these are scenarios, right? So they provide a configuration of the uncertain parameters, the stochastic parameters. And in this case, the problem then becomes this version here, where we're using the scenarios as an approximation of the expected function. Okay. Okay. One example, and this will be the example used in the context of the talk. We'll be using two-stage stochastic linear programs as an example. In this case, so decisions are made in stages, right? So a two-stage model implies that in the first stage, some decisions are made while facing the uncertainty. And then the second stage starts when assuming that all the uncertainty is now revealed and we react, right? So oftentimes we will talk about the first stage decisions as the a priori decisions, so decisions made while facing all the uncertainty. Then somehow uncertainty is revealed and you react, and those are what we oftentimes refer to the recourse decisions. Okay? So here the y variables, they formulate the first stage decisions. And then we have these x variables here that are now indexed by the scenarios, right? Because they are the recourse actions. They are how we react based on the specific scenario that is observed, okay? And what we have here is a linear program, right? So all of the constraints are linear. You might also have, so for example, in the first stage, you are making sure that the decisions are part of this set here. That might involve, for example, discrete requirements, right? So two-stage formulations are oftentimes used in a context where the type of problem that you're facing is invest. And when you are investing, the decisions made in terms of investments are made while facing uncertainty. And then use, right? So first stage kind of represents the investment phase. So for example, you set up a network in the first stage and so forth. That network is then to be used repeatedly to perform some set of operations, right? So the second stage in that case is kind of an approximation of what would occur at the operational level. Okay, so invest first. So oftentimes investments will come with discrete, so the decisions are discrete, right? You're locating facilities, et cetera, right? And then use could also be continuous if you're just, for example, dealing with flow problems as an approximation of the operations, but it could also involve, you could also have discrete requirements on the second stage decisions also. Okay, so this is kind of the setup that we will be dealing with. Okay. So first stage decisions represented by y, right? So these are made while facing all the uncertainty. And then, well, for each S, each scenario in your set considered, you have XS, which are the recourse decisions, how you react if that scenario is observed. Okay. Of course, these decisions need to be made, right? We need to enforce what we call the non-anticipativity constraints, right? So they cannot anticipate the future. So the first stage decisions, they are made without assuming that you know nothing of the uncertainty, right? So they cannot be indexed by S. Whereas the recourse, they react to the uncertainty. So that's why we index them by S. Okay. I mean, if we just take a look at this, these problems can be notoriously hard to solve, right? So first, if you have discrete requirements in the first stage, discrete requirements in the second stage on the decision variables, then you're dealing with a mixed integral program, even in the deterministic version, the single scenario version of the problem. Right? Then, depending on the uncertainty that is faced, the set S, right, the set of scenarios, which is kind of used as the model, how you model uncertainty, right? How the uncertain values of the parameters, in this case, for example, just to highlight what parameters are considered stochastic, well, there is this vector here, right, in the linking constraints between the first and second stage that could be stochastic. The matrix here, right, that targets the y, the first stage decisions could also be dependent on the specific scenario, and even the cost, right, the recourse cost or the cost coefficients here could also be stochastic, right? So you might have a lot of uncertainty, right? A lot of stochastic parameters, uncertain parameters that you need to deal with. And so the set S can be quite large, right? So in order, oftentimes we will generate these sets in a way to at least ensure some form of stability, in sample stability, out of sample stability. And depending on the problem, you might need a lot of scenarios in S in order to be able to capture correctly what the uncertainty is. Okay? So these are challenging. Okay, so we start from there, and depending on the size, depending on the characteristics of the problem, these problems can be notoriously hard to solve. Okay. So, well, this is kind of the question we ended up trying to answer, but I would kind of maybe give it a genesis of the project. We actually started working on this in terms of, can we find patterns in terms of the scenarios, right? So can we kind of have some way of assessing how the scenarios affect the decision making, and then compare the scenarios between themselves, right? So this was, yes, inspired by kind of trying to reduce the number of scenarios, but it can also be helpful for a decision maker to actually understand how the scenarios, right, how the way that the uncertainty is presenting itself actually influences the decisions. Okay, so I will be perfectly frank. When we started, we had not in mind deriving bounds. We had more in mind kind of coming up with a clustering approach where we could kind of assess the impacts of scenarios, but in a decision basis, right? In terms of decisions. Okay, you consider this scenario, and this scenario leads you to make some decisions, or it brings some part of some information to make decisions. Okay. That being said, we did develop the clustering approach with that in mind, right? But then the question was, well, how do we assess the value of the clusters themselves? And then, well, why not derive bounds? So, and this was so we derived 3 different bounds using the clusters that are built. Okay. So this is kind of, can we derive efficient bounds? Yes, this was the question we ended up answering, and the answer is yes. And this is what we propose, this decision-based scenario clustering method. Okay. Okay, what is cluster analysis? Okay, and so this here, I'm kind of using a very nice paper, again, as I mentioned, that is referenced at the end of the presentation. It kind of provides a more mathematical programming view of clustering. Right? So the first step is to identify the sample. What are we clustering? Okay, so you have some sample O, right, of entities. And now you're interested in building clusters of these entities. Then I would say that the main, or maybe the most important steps in the approach is defining step 2 and 3, because this is kind of where, you know, the type of clustering that you end up having is impacted, right? So it's your choices of what is the data and how you define these similarities that are at the heart of how you model the clustering problem, right? So first, the data. So you have your entities, and now step 2 is to associate the data, the representative data for each entity. Okay? So if you're dealing with a population of people, you could consider height, weight, gender, etc. So you kind of measurable characteristics, right, of the entities. Okay? So you select what data you will be basing your clustering on. Okay? So this is step 2. Step 3 is define the dissimilarities. So you need some measure, some way of quantifying how close or far apart 2 entities are from one another. Okay? And the way that you define the similarity in this case is based on the data that was chosen. Okay? So the choice of data will be used in terms of defining the dissimilarity. Okay? So then you build this matrix, right? D, which is the dissimilarity value between all entities to all other entities. Okay? Keep these 2 steps in mind, because I think that these 2 steps are kind of at the core of the main difference of our clustering approach versus other clustering approaches. Okay, so how you define data, how you define the dissimilarities. Okay? Once you've defined it, so the dissimilarities, right? So this is a measure, you need to be able to quantify how close or far apart 2 entities are, right? So the value of each D should be some positive value, right? So each value D should be greater than or equal to 0. The dissimilarity between one entity to itself should be 0, and it should be symmetrical. Right? You could also have a distance, but you don't necessarily need to impose the triangle inequality, right? So you could use distances here, in terms of defining the dissimilarity, but that is not necessary. Okay. Okay. 4 and 5. Now you're modeling, right? You're modeling the problem. So what do you want? What constraints do you want to impose on the clusters? Right? Do you want a partition? Do you want a packing? Do you want a hierarchy of partitions? What are you building in terms of clusters? Okay. You need to choose a criterion, or maybe one, or maybe multiple criteria, right? So you're evaluating your clustering solutions based on what criteria? Are you trying to minimize the dissimilarity between all elements within a single cluster, right? Are you trying to maximize the dissimilarity, et cetera, right? So you're defining the constraints, defining your objective or objectives for your clustering problem. Okay. Choose depending on, now you have the model, right? Now you're able to express what is the optimization, the clustering optimization model. Then you choose an algorithm, you compute, and you interpret. Okay. So this is kind of in a nutshell what clustering analysis is. Okay. So you go through the different steps, you make your choices, and that's how you're defining your clustering problem. Okay. So the types of clustering, this is just to recall, right? So we could have just build a subset of the entities, could be one choice. A partition, right? So a partition is you have clusters. You need it to have at least one element in each cluster. The intersection between all pairs of clusters, so you cannot have one entity common to more than one cluster. And the union should give you the original set, right? So this would be a partition. A packing, it's basically a partition, but you're, just to remind myself, without two, right? So you're relaxing the, but without the condition, oh, sorry, the condition that, yes, the packing, you're relaxing the condition that the union will give you the original set, okay? A cover, I think that's the next one. Yes, the cover, so again, as a partition, but now you allow duplicates, entities to be duplicated among, possibly among multiple clusters, okay? So you relax this condition here. And a hierarchy, maybe the image, right? So you're kind of building this kind of, these sets here, right? So these clusters here, where at each, so you have different levels. In this case, 3 levels are represented, right? And at each level, you have a partition of your original set, okay? So at the level 1, you only have one cluster. At level 2, this cluster has now been separated into 2 and so forth, okay? So this would be a hierarchy of partition, okay? What do you need, right, to build in terms of the clustering will depend on what you're trying to analyze, right? We all agree, okay? In our case, we were interested in building partitions, okay? Okay, so I said choice of data and how you define dissimilarities are kind of the most important steps. A lot of what has been done, right, so when you take a scenario is what? Well, a scenario is a vector, right, of values, right? Each value representing a possible realization, a value of a stochastic or uncertain parameter. Okay? So you have 10, for example, stochastic parameters in your model. Well, a scenario would be, well, put a possible value on each of the 10 stochastic parameters. Okay? So it's one possible realization of the stochastic parameters. So obviously this can be used as the data, right? So you can say, well, let's use as the data the scenario values themselves. Okay, so and then build a dissimilarity in terms of those values. Okay, the values that represent the scenario. What we did was to say, well, what we're interested in kind of interpreting is the information in terms of decisions. So instead of using the values of the scenarios, we will use solutions or decisions. Okay. So what was done here is that it kind of used the classical predict and optimize type of approach, right? So if you're using a predictive model or an oracle or whatever, right, and you predict a given scenario from your set, well, you would solve, let's say, the deterministic problem based on that specific scenario. Okay, so I predict scenario 1, right? I would then solve the problem as a deterministic problem using scenario 1. I would get solution 1. Okay? So this is what we use in terms of the data. Okay? So the data now would be to use the first stage values of the solution that you get when you predict, then optimize. Okay? So this is kind of the first, so this is our choice for, and we would use, in this case, use a single solution, but at the end, in the concluding remarks, I mean, obviously you could use multiple solutions, okay, depending again on the type of application that you're interested in doing. So these are these solutions here, Y star S. Okay, so it's the optimal solution, right? Assuming that you're able to solve the problem to optimality, the optimal solution that you would get when you predict scenario S. Okay? Now, predict, then optimize, that means what? Well, that introduces the possibility of an error in the prediction, right? So if I predict scenario 1, kind of go through the steps, right? So I predict scenario 1, I would solve based on scenario 1, get solution 1, implement that solution, but then scenario 10 turns out to be observed, right? Well, and this is where the dissimilarity was measured in this case. We actually measured it as a function of the opportunity loss or the implementation error. Okay? Yes, yes. So the idea here, right? So the dissimilarity between two scenarios would be to say, well, if I predict scenario 1, but scenario 2 turns out to be observed. Okay, so if I predict scenario 1, I would solve the deterministic problem based on S1. I would get Y star S1, but then S2 turns out to be observed. Okay? So what you have here is, well, this would be the optimal value if I had predicted correctly, scenario 2. And what I have here is the value of Y star S1, right? So the characteristic solution of scenario 1 in the context specified by scenario 2. Right? And this will necessarily, if this is optimal, there is necessarily a gap here. Okay. So this is what we call the opportunity cost, right? And then for the dissimilarity, because again, if you predict S1 and S2 turns out, vice versa, if you predict S2 but S1 turns out to be observed, right? The cost might not be the same, right? So the dissimilarity is actually the sum between the two. Okay? And this is how we define the dissimilarity. Okay, so we're using the implementation cost as the way to measure the dissimilarity or similarity, right, between two scenarios. Okay, does this make sense? Okay. So kind of just some theoretical, yes?
Yeah. It's based on the objective function, but this
Yes.
Could you do something as well based on the first stage decisions?
Yes.
Like
absolutely, absolutely. You could also look for characteristics that are common to the two solution vectors, right? Absolutely, absolutely. Okay. Okay. This was kind of just trying to come up with an argument, a theoretical argument that could support a little bit this approach. So a proposition, but I think that the corollary is actually more interesting, right? So if you define G, right? So the original function as the two-stage linear stochastic model previously, and somehow you're able to identify all of the optimal solutions, right? Characteristic of a given scenario. Okay, so suppose that you have these sets here. So those are you're grouping all of the optimal solutions associated to a given scenario. Well, if somehow there is a common solution to all of them, right, then is also optimal to the stochastic problem. Okay? So if somehow it turns out that a single solution is common to all optimal for all deterministic scenario-defined problems, then it's optimal. Okay? First, this is not easy to determine, right? And I'm not expecting this, right? So this would be very doubtful that in many cases this will be observed. However, and this is where I think the corollary is a bit more interesting, is that you can also, the result also applies on the cluster, right? So on the cluster, if you take some cluster C of S, and again, the condition is met, then the conditional expectation on C is also minimized by the Y star. Okay, so actually, this gives credence to the idea, yes?
Regarding to the constraint you mentioned in the clustering analysis,
Yes.
The scenarios are considered in the Euclidean space.
They are, yes, yes.
We can consider them in the manifold space with
Okay.
the similarity in when the distance is not Euclidean but geodesic
Okay,
or so on.
okay, okay.
The assumption
Yeah,
we consider here for the theoretical purpose is specifically based on the Euclidean space.
it was, I think implicitly it was, yes, yes, implicitly it was. Yeah. Okay, so so this kind of was a result that motivated the idea. So if somehow we can identify subsets or clusters of scenarios, well, this kind of gives us a good idea that we're at least able to eliminate some scenarios in the extreme case, right? So this was kind of the general approach. Obviously, we don't expect to find this in many problem instances, but the closer we get, right, by minimizing. So now that the idea is to say, well, kind of if I'm able to, it makes sense to minimize that dissimilarity, right? If I seek clusters that minimize that dissimilarity and actually find clusters where the dissimilarity as measured through the opportunity loss function is very, very small, then, I mean, we're finding good patterns, at least in terms of reduction. Okay, so going through the steps, obviously our entities are the scenarios. The data are these solutions here, right? So again, we're using one single solution, but again, I'll discuss a bit more. We could have used multiple possible alternative solutions per scenario, right? So you get this matrix here. The dissimilarity is based on the opportunity cost function that I mentioned previously. So we're interested in building partitions in this case. And the way that we are doing this, right? So again, kind of the idea here was to minimize the dissimilarity within each cluster, right? So basically, this turns out to be, you know, a max cut problem to be solved. Okay, so and we used graph clustering techniques in order to solve this problem. Okay. Okay. How many clusters? This is an important question, right? So how many clusters should you find, right? So again, the way that we did it was kind of use different values and then build the clusters based on a varying number for a varying number of total number of clusters, and then choose the appropriate number, okay, a posteriori, right? And the criteria that was used in order to choose is the silhouette score. Okay, so I'm not sure if everyone is familiar with what the silhouette score is, but it's a score that you can compute for a solution to the clustering problem, right? And so the idea here is to take, so you associate a value, so you have the silhouette score value for each scenario, right? And then the value for the solution is summing up all of the silhouette score of all the scenarios, okay? So what is the silhouette score? So you take a scenario S. Okay? S, let's say, is in a cluster CK. Okay? So it was put in a given cluster. Again, it doesn't appear anywhere else because we're building a partition. And then you measure these two quantities here, AS and BS. AS is so you're summing up the dissimilarity between the scenario S and all scenarios S prime that are in CK. Okay, so you're considering all these scenarios that are within the same cluster. Again, divided by, you're normalizing the value here. Okay? BS, right? So this is So this is the value AS. VS is to identify the closest alternative cluster. Okay? So you're considering all clusters L that are not K and trying to identify the one that is closest to scenario S. Okay? And again, you're using the sum of the similarity between S and all the scenarios contained in the alternative cluster. Okay? And you're identifying the minimum, right? So the one that is closest to based on the dissimilarity measure. Okay? Then the score. So obviously you want this to be as small as possible, and you want the B value to be as large as possible, right? So that would be a good score for a given scenario. Okay? So then the silhouette score is the difference between the value B and A divided by the max. Okay? So this is for one scenario, so which gives you the following result, right? If the two values are equal, the score is 0, the silhouette score is 0. If AS is indeed smaller than BS, then you have a value of 1 minus the ratio between A and B. And if it's the reverse, it's the ratio between B and A minus 1. So it gives you something between -1 and 1. Okay? Obviously, the closest you are to 1, the better it is. Okay, the better the score. Okay? Total, so the total, so the value, the silhouette score for a solution, for the clustering solution, would then be the sum of all silhouette scores for all scenarios. Okay. So again, the way that we did or answered the question of how many clusters was to say, well, run it for 2, 3, 4, 5, 6, et cetera, for some arbitrary range of values, right? And then compute the silhouette score each time, and then identify among the range the number of clusters that provides you with the highest silhouette score. Okay, this is how we identified the the number of clusters. Okay, so now the bounds. Okay, so the bounds are fairly simple. The first one is kind of an elected approach, right? So you basically go through the clustering analysis steps. You get the clusters. Once you have the clusters, you nominate one representative. Okay, the one that is nominated is the metoid, the one closest to all other elements within the cluster. Okay? So this is kind of reducing the number of scenarios, right? So you build the clusters, identify a single representative, create a smaller two-stage model, but by only considering the representative scenarios from each cluster. Associate the total probability of the cluster to the representative, right? And then solve that reduced size model, okay? Get a solution, then take that solution, evaluate it over all scenarios in S, and that gives you an upper bound, okay? So it's kind of scenario reduction through the clusters, through the use of the clusters. The lower bound. Well, the lower bound here, so is everyone familiar with the value of perfect information in stochastic optimization? So the idea here is that if you relax the non-anticipativity constraints, okay, so if you assume that which means what? Which means that you're assuming that the first stage decisions can actually be made based on the information regarding the uncertainty. So you can actually tailor the first stage decisions based on the specific scenario. Okay? Suppose that you solve all of so to get the solutions we saw previously, right? The Y star S1, 2, 3, etc. Okay? If you actually compute then the value, right? The expected value of using all of those solutions based on all of their associated scenarios, right? That is a lower bound. Okay? It's a lower bound based on knowledge of the future, right? So it's kind of that you relax those constraints. You assume now that you're able to predict perfectly, right? And so you can tailor your first stage decisions based on perfect anticipation of the scenario. That gives you a lower bound, okay? Cluster here is actually the same type of bound, right? But instead of completely relaxing the non-anticipativity constraints, you partially relax them. Okay? Suppose that you're able to anticipate, right, that cluster, not the scenario, but the cluster. So if I anticipate cluster 1, let's say, then the best I can do in that case is to solve, right, based on that cluster, right? By reducing, if I assume that I know this future, right, I would then solve using the expected function conditional to the cluster, right, and get a solution that is tailored for that specific cluster, right? And I do this for all of the clusters. Then again, computing the overall expectation would give me a lower bound. Okay? There's an important note here. So if you think about it, right, so what would be the best bound in that setting? Well, the best bound in that setting would be somehow if I'm able to recreate in each cluster the overall problem, right, I would get a solution that is closest to the optimal solution if I consider all of the scenarios in S, and all cluster solutions would agree, right? They would all somehow turn out to be the same solution. Okay? So in this case, right, so if you think about it, what you're trying to create in order to get the best bound, at least intuitively, is within each cluster a good representation of the overall set. So in order to improve the quality of this bound, instead of minimizing the dissimilarity within the cluster, we maximize the dissimilarity within each cluster. Okay? Trying to come up with the most diversity or dissimilarity within each cluster that we generate. Okay? So this was just to compute the two last bounds, right? So we basically just reversed the objective in our clustering problem. Okay? Cluster upper bound. So again, this is using, again, the clusters. Now you're solving for each cluster separately, a reduced sized two-stage stochastic model. You get solutions, right, that are representative of each cluster. These can then be evaluated over all the scenarios in S. And this, again, you identify the best one, right, the minimum one. And this gives you an alternative upper bound. Make sense? Okay. So 2 upper bounds and 1 lower bound by leveraging directly the clusters. Okay. So we tested this out on two models. These are taken from the literature, right? So the first one was easy to solve. We could actually compare the results with the optimal solution. So this was useful just to kind of validate numerically the different bounds that we were proposing. So this is a biweekly fleet planning model. Again, it's both models are 2-stage. Here are the decisions that so you have a set of locations. The decisions that you're making first is you're deciding the number of vehicles to be deployed at terminal I at the beginning of the first week. Okay. First stage is the first week, second stage, the second week. You know the demand in the first week, but in the first week, the demand for the second week is stochastic. Okay, so this is the stochastic parameters are the demand for the second week. And then you decide the number of loaded and empty vehicles that are, distributed throughout the locations. So Xij and X tilde Ij, these denote the number of loaded and empty vehicles that will be traveling between I and J. Okay. And Z tilde I, this is the number of vehicles made available at terminal I at the beginning of the second week. So for the second week of planning. Okay. I mean, the constraints are fairly simple. So whenever you send a loaded vehicle, that generates a revenue, right? So here in the list, you have a revenue for each loaded vehicle that is sent, right? And then the rest are costs. Okay? So the cost of assigning vehicles or deploying vehicles at the terminals, the cost of sending empty vehicles between the locations. These are the flow conservation constraints, right, at the different locations, beginning and for the second week. And here you're simply stating that the number of loaded vehicles that are sent is less than equal to the demand, okay, of flow to be sent between 2 locations. Okay, so this is the first stage. Second stage, basically the same thing with one exception, is that you're adding a cost here, Wj. So if somehow at the end of the second week, you have less vehicles at each of the location with respect to the first week, you pay a cost. Okay, so there is an incentive to end the second week with the same amount of vehicles that you started off at the beginning of the first week. Okay, but the rest is simply the same one. 4 instances from the literature, 25 locations, 100 scenarios. These were the first set of instances, easy to solve. We were able to compare to optimal solutions. Second problem is a bit more challenging. So this is a classical stochastic network design model. Okay, so you have commodities, or a commodity in this case is an amount that a flow that needs to be transported between a given origin to a given destination in a network. In this case, the volume is assumed stochastic for each commodity. And the 2 stages are as follows. In the first stage, you need to design the network. So you're choosing which arcs you put or you include in your network. This is done while facing all the uncertainty. The uncertainty in this case, demand volumes is uncertain. And capacities of the arcs can also randomly change, right? So when you select an arc, the capacity of that arc might also randomly change. Okay, so these are the 2 sources of uncertainty. First stage, you design the network. Second stage, well, it's a multi-commodity flow problem based on the network that was designed. Okay. Again, these were instances taken from the literature, and in this case, 96 scenarios included in the set. Okay, so in terms of scenario, and this again, I'll mention this at the end of the presentation, relatively limited, right? 100 in one case, 96 in the other. The number of scenarios here were fairly small, but still the instances were extremely hard to solve. Okay. At least not the first one, but this one is. Okay. So these are the results on the first set of instances. So the easy instances. So what you have here. So this is the quality of the medoid upper bound, right? So the first upper bound technique that was mentioned. And what we're comparing here is first the decision-based clustering compared to just, Monte Carlo, constructing the clusters through the use of Monte Carlo sampling, right? So 10 runs. So you construct the partition by selecting randomly the scenarios to keep in each cluster. Okay. Gap versus the number of clusters. Okay, so you're seeing that what we're seeing here is that the medoid upper bound is actually giving us very good results in terms of gaps, at least beyond 6 clusters. In this case here, we need a bit more, 10. In order to reach a close to optimal solution in terms of the quality obtained. In the first 3 instances, at 6, we were already down a lot in terms of the gap. So that was quite nice. So again, reducing from 100 scenarios to 6 in this case, let's say, and getting a solution that is close to optimal. Okay, so I mean, the clusters were providing a lot of value. I mean, if you're randomly generating the clusters, again, the bound is a bit all over the place, but this was to be expected because there is no, you're just sampling, right? So the clusters are generated randomly, right? So there is no consideration of the actual problem. So this was not, this was to be expected. The lower bound was interesting. So here, actually, the random approach was doing a good job, right? So constructing, right, the clusters randomly and doing 10 runs. Yes, might not have mentioned this previously, right? So these are the average results over 10 runs of the random clustering approach. So here we were expecting that at least the lower bound would be better, right? So through the 10 rounds, we would get some better results. What was interesting to see here is that by maximizing the dissimilarity when we construct the scenarios. So again, the way that these 2 things are compared, right? So the random is 10 runs. So you're performing 10 times the clustering. Whereas the decision-based, you're doing the clustering, it's a deterministic approach, right? So you're doing it only once, right? So it's one single run. So actually, in this case, the lower bound, the quality of the lower bound using the decision-based clustering was actually doing a very good job in terms of matching the random approach, right? So in terms, it was doing a good job of ensuring that the clusters were dissimilar enough in order to get us to obtain good bounds. In this case, the best bounds you get is by only only having two clusters, because that is, if you think about it, the least, in terms of the relaxation, is when you relax the least the original model, right? So the more clusters, the more the original model is being relaxed. Okay, so two clusters in this case provides you with the best alternative. On the harder problems, right, the network design problems, again, so I divided in these two tables, those that were solved using CPLEX versus those that CPLEX was unable to solve. In order to make the times comparable, what we did was to just account for all of the time devoted to perform the clustering, compute the bounds, et cetera, right? So you just compute or tally up the total time devoted to all of the steps to obtain the bounds, and then give CPLEX the exact same amount of time. So in terms of time, the runs are comparable, okay? So these are the cases where the CPLEX was able to solve. What was interesting to see here, again, was the Medoid was doing a fairly good job. It was finding close to optimal solutions on almost all cases, right? And again, and here you have the number, the optimal, based on the approach of the silhouette, the use of the silhouette score, right? The optimal number of clusters that were being used. So the number of clusters varied between 2 and 11, right? So 11 in this case, mostly 2, sometimes 3, 4, et cetera. So the Medoid was given the number of clusters, reducing the size of the model, solving, and still getting a very good solution in the end, okay? So these are for the easy instances. These were the harder instances, the harder network design instances. Again, the runs are being compared in the same fashion. The gaps here are larger, right? So these were instances not solved to optimality by CPLEX. But again, the Medoid was doing a very good job. Cluster bounds was also doing a better job actually than CPLEX. Okay, so here you have the improvement on the lower bound side. Okay, so in almost all cases, sometimes the lower bound was a lot better, other times less so. Here it was only 0.88%, but here, for example, or here, you have an improvement of 23%, right, for the lower bound. So again, depending on the instances, the improvement would vary, but this was providing us with some appreciable value from the clusters. Okay, so bounds worked, at least on those two instances. We had some nice results. I think that this idea of interpreting, so scenarios are what? Scenarios are information, right? If you think about it, it's information used to model uncertainty. Okay? Using this idea of the opportunity loss, the implementation cost, I think is a really useful tool to interpret how the information is actually impacting the decisions. Okay? And then finding scenarios, for example, that are for which the solutions are good proxies for one another, right? That kind of tells you that this type of information is leading you to make similar, quote unquote, decisions. Okay, so I think this was and it's a useful tool also. I might mention some ongoing work that I'm currently involved in, where we're basically again reusing this idea in an algorithmic sense, right, in order to improve the efficiency of certain algorithms. So future work. So the clustering here was not done in terms of trying to solve directly the scenario reduction problem. This is This was kind of done as analyze first, use second, okay? But there is in this follow-up paper here that has actually now been published, we actually kind of showed that this idea of using these representative solutions can actually be leveraged when you're directly trying to solve the scenario reduction problem, right? So when the idea is to say, well, I'm clustering with the ultimate purpose of finding these good representative scenarios that can then be used to reduce the set. Okay, so this was the follow-up work. In terms of extending, so I think there's still a lot of work to be done when you start thinking about it, right? So what you're doing, again, you're associating decision data to scenarios. Okay. Here we use one single solution for each scenario. You can use alternatives, you can define, right, the dissimilarity actually can be defined in various ways, right? In this case, it was defined as an optimization model, right? A deterministic optimization model where you hard fix the first stage and solve on the remaining dimensions, right, of the second stage. That being said, you can fix part of the recourse, right? You can do different things here. You can use the solution to define another type, an alternative type of restriction, right? Maybe where you're using self-fixing approaches, et cetera, in order to assess patterns between the scenarios. So this, I think, is also interesting work to be done in the future. Just the references. So the clustering analysis, this was taken from a fairly now old paper, but that I find quite useful by Pierre Hansen and Brigitte Jomard. And then this was where the clustering approach was published. Thank you for your attention.